Hello, our lab project is binary phase shift keying. So we started with making a multisim circuit that was given in our lab manual. The problem with that circuit was that it didn't have the right transistors that were available in the multisim library. So we found the multisim transistor alternatives from the internet. There are many helpful sites where you can find those. So it required a lot of trial and error, but in the end we found a uh, good transistor combination that helped us find a good output. So here we are trying using trial and error and using different transistors to get a good output. Here you can see the output. PSK phase shift keying, through its name you can see that it changes the phase depending upon the input. So binary phase shift keying is a simplistic model of that, and it's still widely used because of its simplicity. It is used in RFID scanning, and the phase shift keying is used in wireless LANs and Bluetooth application. Here is a demodulator circuit. It has one op-amp IC. Here in the second you will see the two transistors. These transistors are switched on and off depending upon the message signal, which turns them on and off. As you can see, there is one PNP transistor and one NPN transistor. So they work in complementary form of each other. In the next circuit, you'll see me plotting the real components while showing them. Here is me marking the circuit. So this is a sine wave input. That will be the carrier wave. It is a high frequency wave, which will be 5 volts and 1 kilowatts. These are the values given in the lab manual, but in the end we found better values than this. This is the carrier frequency, which is obviously higher than the message signal. We'll see that in a second. This is the carrier frequency is 1 kilohertz. In the end, we found that it was the good frequency was 2 kilohertz. So this is the message signal, which is a square wave at 400 hertz, which is lower than the carrier frequency. This is a 10K transistor. There are many apps on the Android market to name these circuits using the color coding, which makes it really easier. This is the transistor. I think this is the SK100. The key point to note here is that the notch signifies the emitter, and the middle one will always be base, and the other one left will be the collector. This is a PNP SK100 transistor. There are two transistors used here, SK100 and SL100. Here you can see the notch signifies the emitter, the middle one will be always the base. This is SL100, the PNP transistor. The thing to note here is that this transistor won't be available in the multisim library. You have to find alternative, and depending upon your application you need to use trial and error. This is the 1 kilo ohm resistor. This again a 10 kilo ohm resistor. As you can see by now, the circuit is really symmetrical around the op-amp till about here. This is a 741 op-amp. This is the reference circuit of that 8-pin IC. 4 and 7 will be the plus and minus input, 4 being the minus 12 volt or 15 volt input, and 7 plus 12 to 15 volt input. The feedback resistor is 10 kilo ohm. Here we get the BPSK output. Here this is the modulator circuit of BPSK. Here is the circuit that we made. This is the given lab manual inputs. The problem and the challenge faced in the lab was that we had to make the circuit quite many times. Here you can see the output. So this is the making of the circuit. So the challenge we faced in the lab was that there were a lot of discontinuities in the lab, and we couldn't save the circuit because we had to return the components. So we made the circuit quite many times from scratch. It delayed our process. So this is the binary, this is the modulator circuit. I'm showing a time lapse of it. So I'm grounding the transistor. I'm taking two individual wires from the emitter of both PNP and NPN. This way, as you can see, I'm taking two wires individually and connecting to the ground. This is far less complicated if you follow the diagram crudely and directly. So this makes it really simple. The key thing to notice here is that no wires touch each other, so to cause a short circuit. During our first application, we shorted the power source, and there are 3 lights on the power source. If the light are turned off, it means that you have short circuited your circuit, and you need to check what the problem is, and you have to switch off the power supply bin. This is the input. It was a really complicated circuit to make on a breadboard. If we had time, we could have made it on a printed IC, and it would have been far easier. We just had to put the components in, and we could have had the circuit in a printed IC. Because of its complications, we had to change the position of IC quite a number of times. As you will see in the demodulator circuit, there are 2 op-amp circuits. One of the ways that we found that was really effective was that we put the ICs, as you will see, in the opposite directions. to each other, which made it far easier to make the whole circuit. Here are the two inputs, and this is the feedback resistor. These are the inputs. This would be the positive input at the 7th pin. This is the negative input at the 4th pin of the op amp, 741. So we didn't actually follow the lab manual's input. We had to vary the inputs. This is Aman putting in the inputs. So as you can see, the three lights glowing red, that means it's fine, the circuit is fine. This circuit, as you can see, it's clipped at the top. So we varied the inputs. As you can see, one of the both of those phases are clipped at the top. So still clipped. This is because the transistors have higher voltage input than it is necessary. So we changed the input, decreased the values of the message signal and increased the carrier frequency. This is a really good output. These are the values. So then we start with the demodulator circuit. The one of the things that you can do for a good output or the demodulated output is to ground the modulator and demodulator commonly. So both the grounds of the modulator and the demodulator will be common. Here you can see the diode. The thing to notice in the diode component is that the line that will be there in the PN junction signifies the line in the diagram. So there are two op amps in this circuit. One of the things that we found that was really helpful was putting the op amps in opposite direction to each other, as you'll see in the circuit when I'll show it. This is the feedback resistor. The major thing to notice in this circuit is that it has a potentiometer. One of the challenges that we faced in the circuit was that we didn't know how to connect the potentiometer. And during our first application of the circuit, I actually burned the circuit. As you can see, the line signifies the P junction line in the circuit. So I burned the potentiometer because I connected it in properly. So the key thing to notice here is that the middle wire or the middle socket or the middle pin on the potentiometer goes into the input. This 0.1 microfarad capacitor is not a condensator type capacitor and therefore non-directional. But the thing to notice is that the diode is, this you can see as a potentiometer sketch, reference sketch. The middle wire will always be connected to the signal. As you can see, it goes to the op amp. The other two wires can be connected as you wish. So if you wish to connect the upper wire to the VCC input of 5 volts or 6 volts, you can connect it to that, and the other wire will be connected to the ground. So the signal wire will be connected to the non-inverting part of the 741 IC the third pin. So the middle is a signal, and every other wire is actually, one of the wire is optional. So if you one of the ground is optional, you need not connect to the ground in the potentiometer also. Some circuits have only two inputs from the potentiometer. So first is the difference amplifier part, the second is the envelope director, and the third is the comparator. This is the envelope detector part. Remember to connect the potentiometer properly and ask the lab attendant for help. And as and when you smell burning, you just switch off all the circuits. So this is the demodulator output. As you can see, there are two op amps. These are the three lights. So this is the VCC input of 5.96 around 6 volts. This is the first input given in the lab manual. The main challenge in this lab was that we didn't have the modulator circuit at this time. So I just put the PSK input, took the PSK input from the oscilloscope or the function generator. This is the input. This is the demodulated output. It's a square wave again. In a second you'll see me put the PSK output and the PSK demodulated output. These are the values that I found was good for these, and actually you have to change the potentiometer to get a good output. In the end I'll show you how you change this is a good output, as you can see. So this is the PSK input and the demodulated output. I did not use binary phase shift keying because we didn't have the circuit. This was a challenge faced in the lab because there were many discontinuities in the lab and we have to make the circuit from scratch again and again. So this is by varying potentiometer we can get a good output. As you can see, I'm varying the potentiometer and it goes to the highest limit of the square wave to the lowest limit. There's one sweet spot in this, and you can find good square waves. You have to find that sweet spot. This is common in ASK modulation also. And here you can see getting the square waves. There is a sweet spot you have to find where this is at the point that you find good square wave. This is our DCS project, and thank you for watching the video.